video 2 of the series. This is where we left off last time, looking at the phase changes. Remember, as your temperature remains constant as you go through the phase changes. You should have already, or you will do this lab in class. So you will actually get an opportunity to look at how these temperatures remain constant here. But we'll go ahead and keep going. The collision model. In order for our reactions to happen, you need to have, let's go back. In order for our reactions to happen, you actually need collisions to occur. Molecules are not going to react with each other unless they actually meet each other. We call these collisions. Collisions must have two things. Well, first, let's look at this. This is one of our molecules, and this is going to be another one of our molecules. And let's say you get a reaction when one molecule is inside the other. Right? Here is our reaction. Now, two things must happen in order for us to get a reaction. First is that your collisions must have enough energy. So, if I'm here, and I throw the ball like this, like, is this going to get into the basket? No, right? Because I don't have enough energy. And until I have enough energy, I'm not going to be able to get that collision. The second thing you must have is the proper orientation. Molecules need to be lined up the correct way. If they're not lined up the correct way, even if they have enough energy, a reaction still isn't going to occur because the molecules need to meet in the proper way. Again, no collision. Only when you have the correct energy and the proper orientation can you get a reaction to occur. Now let's go back and talk more about activation energy. Activation energy is the minimum amount of energy required for a reaction to occur. Now these are two, this top definition here is a little bit more higher level. So let's look at this second definition. That would be the definition I want you guys to write down in your guided notes. Minimum energy required to produce an effective collision or to produce a reaction. For instance, these are spark plugs from your car. If I put gasoline in my car, is my car going to just go? Is it just going to drive? No. No, right? I actually have to make something happen so that we can get, again, up over that activation energy barrier. Gas is not going to just combust spontaneously in my car. I have to have these spark plugs in order to start the reaction, get my car going so that I can start driving. Okay, here is the exothermic process. We're going to review this again. Here's that activation energy that we were talking about, our activation energy barrier. We have to have at least this much energy in order for this reaction to occur. Again, our energy of our products is lower than the energy of our reactants, so here is where we are storing our energy. If you were holding this reaction in your hand, because it is exothermic, it would feel
hot.
Good. All right, and then endothermic again. Same thing here. This is the minimum amount of energy that we have to overcome in order for our reaction to occur. Our energy is being stored in our products because the energy of our products is higher than the energy of reactants. So this reaction would feel
cold.
Good. All right. Let's talk about this phase change diagram. You've seen this phase change diagram before. I will tell you on your notes the arrows are swapped. Not bad. The arrows are swapped. So go ahead and swap these terms on your paper. You've seen this before. We can review this later in class. Let me just hold it up there for 30 seconds or so. Maybe not.
I can press pause.
You can press pause. I'm going to keep going. Okay. All right. Processes that occur, that move to the right here, that's where you're adding energy. And then, of course, processes that move to the left, that's where you are removing energy. Let's talk about some of these things. A phase diagram represents phases or phase changes as a function of temperature and pressure. Your trickle point is where your substance can exist as a solid, liquid, and a gas. And let's go back. Here's your trickle point. At this point, at that particular pressure and temperature, it's just as likely that your substance will be solid, liquid, or gas. Go back here. Critical point, a critical temperature and pressure where you sort of mix the lines between a liquid and a gas, and your gases tend to sort of take on liquid properties. Tends to be higher energy and high pressure. Okay, thermochemical calculations. We're going to look at the one formula that we're going to use for this unit when we're calculating heat energy. We're not going to get any more complex than this one equation. We're going to try and keep it pretty simple. Again, let's review. We measure our heat in joules and calories. And we're going to talk a little bit about specific heat before I show you guys the exact equation. Specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And what's significant, and you guys will see this later, and you see the chart in your notes, is that each substance has a different specific heat. Each substance requires a different amount of energy for that temperature, that 1 degree's temperature raise. So that becomes a significant part of our calculations. This is the equation that we're going to use. Q equals M times delta T times Cp, or if you rearrange your equation, C equals Q divided by M times delta T. C is the specific heat. You will either have everything except this, and you'll be asked to find this, or this will be given to you in a problem, or you have on your notes right here, you have a little chart that shows you what the specific heats of different substances are. Q is the heat lost or gained. This is measured in joules. This is your heat energy lost or gained. Delta T means temperature change. Change is this delta, this Greek symbol delta. Change in and then T for temperature. And then the last thing here, mass measured in grams. Here's that chart that you guys will see on your notes. The amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius, that specific heat. And then here's a list of materials that we're going to use in this class. We're not going to use anything else other than this unless I give it to you in the problem specifically. So let's go ahead and try a problem. Gold has a specific heat of 0.129 joules per gram Celsius. How many joules of heat energy are required to raise the temperature of 50 grams of gold from 22 degrees Celsius to 42 degrees Celsius? And will you go ahead and rotate the camera here? I'm going to try and do this off the side. Just like we've seen in previous problems, the first thing I want you guys to do is to, off the side, write out what your variables could be. We had Q, so write Q equals M equals C equals, and delta T equals. And then go ahead and draw this information from the problem itself. So, can you still see the whole problem? Now let's go back to the problem here. Gold has a specific heat of 0.129 joules per gram Celsius. So specific heat, C, is 0.129 joules per gram Celsius. How many joules of heat energy are required to raise the temperature of 50 grams of gold? So we can say mass is 50 grams from 22 degrees Celsius to 42 degrees Celsius. The change in that is a 20 degree change, 22 to 42, 20 degrees. So our delta T is 20 degrees Celsius. Then we go back to the equation that we were given earlier. Let's go back. this is the equation we're going to want to solve right here because our Q is unknown. So we set this up. Q equals M C delta T, 20 degrees Celsius. What is the first thing you do when you get to this point, Abby?
Multiply.
Wrong.
I don't know.
Cancel out your units.
Cancel out your units.
Good. All right, so we cancel out our Celsius, cancel out our grams, and then we multiply. 20 times 0.129 times 50. Let's plug that into our magic box. And we get 129. And then I ask you the question, 129 what? And you say joules.
Joules.
Why joules?
Because that's all we have left.
That's all we have left. So 129 joules. There you go. That's our first answer. Good. Now that was the first problem that you guys had on your sheet. So let's go ahead and do the second problem as well. An unknown substance with a mass of 35 grams absorbs 1,450 joules while undergoing a temperature increase of 90 degrees Celsius. What is the specific heat of the substance? Again, off to the side, write out what all of your variables could be. Can you see this?
Mm-hmm.
Q equals, M equals, C equals, and delta T equals. What here, Abby, is M?
35 grams.
35 grams. Good.
Do this to me.
Q is our heat energy. That's the 1,450 joules. And then, Abby, what's our delta T?
90 degrees Celsius.
90 degrees.
Celsius.
Celsius. Thank you. Oh, let's go back. So we're going to look at this second equation here because C is our unknown, our specific heat is our unknown. You set that up, Q over M times delta T, so Q, 1,450 joules, over M times delta T, which is in our 90 degrees Celsius. And this equals, wait for it, .46. And then I say 0.46. What?
Degrees Celsius.
Okay, joules.
Joules per whatever.
Per
Grams.
grams
Celsius.
Celsius. Alright, joules per gram Celsius. Those are your units for specific heat. The homework assignment that you will receive is 6 of these problems. They're not terribly difficult. It shouldn't take you more than maybe 20 minutes. Maybe 20 minutes. If you need any help with that homework, please go ahead and let me know. Go ahead and work on that now while you have this information. And we'll come back with the rest of your thermochemistry stuff. This is where we're storing our energy. We're storing our energy in the reactants. We get up. Hey, homie, cuz, come sit down.